Thank you. All right, let's get started. So happy Tuesday, and of course, happy Earth Day. So unfortunately, I don't think RCC is doing anything. Again, you can advocate for me for next year for lack of funding and support. That's why nothing happened, but I think there are some community events going on. Check those out, like Blue Heron Park and Talent, I think this weekend, and Ashland's doing something big, I think, with SOU. And I think that's also on Friday. So yeah, look for that. Nice weather, so activities. And then, if you can believe it, we're flying through the quarter. And so we'll have our midterm next week. And so similar structure, at least in terms of that we'll review on Tuesday. We'll have our midterm on Thursday. I'm trying to look at last year's exam. So I'm inclined, looks like last year's exam was pretty free response heavy, so maybe I'll add some multiple choice to it, but I'll try to keep the exam easy. I mean, there's less of you in the class, so I feel less like I need to break a hard curve with that. And then quizzes, I did grade, but I didn't put the grades into the grade book, so I'll do that and hopefully hand those back in lab or obviously on Thursday. But the quizzes look good. The only thing I'll say right now at least, so quiz 1 on the acid-base stuff, most people did that really well. Question 1. And like I said, most people got it right, so you had to find the moles and then do the reaction. And there was some like neutralization reaction. Yeah, so it was, we'll just quickly kind of review it. So it was acetic acid plus NaOH. And then you had to recognize, right, that you did your reaction and then also made acetate, which most people recognize that. And then you could use Henderson-Hasselbalch, right? So the pKa plus your log of your base over acid. So, right, plugging in your acetate versus how much was left after the reaction. But that looked really good, so most people got that right, and the rest of the quizzes looked pretty good. So like I said, I'll try to hand those back sooner rather than later. All right, so let's do our last chapter before the midterm. So doing some redox reactions. Oh, one more announcement, sorry. So I forgot, so next week for lab, again, just a reminder, so lab next week. So this week we'll be doing the electrolysis lab, which actually does fit nicely with what we're working with. And then next week we'll do makeups on Tuesday. So if anybody needs to make up something, let me know. Otherwise, right, the Thursday class that I missed will meet on Thursday for makeup for the lab that I had to miss. So we can meet on that Thursday, or, you know, if you for some reason couldn't make it Thursday, Tuesday would work. If you need to do a makeup on that Thursday, also available. So next week will be makeup labs. So just email me if you need to do something other than the acid deposition lab, of course. All right, so now let's dive into redox reactions. And some of this could be a review. I think we've kind of slightly touched on the subject. And so we can recall, like, what types of reactions tended to be redox. And we can think of some examples. So can anyone think of some examples maybe?
My first thought was iron rusting.
So iron rusting. I always forget which is the more common one. I forget if it's iron 2 or 3 is oxide. And so, okay, good example, right? Type of reaction combination. So again, just kind of trying to frame ourselves, so looking at also, right, we have a metal source. Other reactions that we remember maybe, might have to dig back to like first quarter, some of the labs that we did, or other types of reactions. Do you remember the copper lab at all? And like the last step, what was that last step? Do you remember? What two things you added? I mean, it was an aqueous solution, but then, because I don't know if you remember, so I'll give you some hints. So we had the blue copper sulfate solution, and then how did you get the copper back out? Do you remember what metal you put in?
It could have been pretty much any metal.
Yeah, zinc. But yeah, so you're going to recognize later that maybe we could have selected another metal that could have replaced it. But yeah, so we use zinc specifically in the lab. And so again, we're kind of remembering what type of reaction this was. So a single replacement. And then yes, this goes back to our activity series lab where you were trying to do essentially single replacement reactions, right? Testing whether it would occur. And so now we'll kind of answer, right, the why, at least a little bit more in depth. All right, that's good. And then of course, I'll just put another type, obviously, right, the classic combustion. So this is more a combination, but then we can think about any organic reaction. So let's just do ethanol plus oxygen, right, gives us CO2 and water, so combustion. All right, so all those, again, are just types of redox reactions, so it helps us to recognize, right, that anytime we have these reaction conditions, we probably have a redox reaction. And then I think we've defined this before, but again, we'll just go over it so we're all on the same page. So reactions in which electrons are transferred then from one atom to another are called oxidation reduction reactions or redox reactions. And then if you recall, so we have atoms that lose electrons are oxidized, and atoms that gain electrons are being reduced. And then we could also use the term, so if something is losing electrons, then this is our reducing agent. So again, supplying electrons. And then if it's being reduced, it's our oxidizing agent. So again, receiving electrons. And so then we might have to recall the process by which we assign oxidation states. And we could skip down. So let's go back to our rules for a second, just so again we can recap. And so we have our oxidation rules. Again, just a friendly reminder. So fluorine, and this is in a compound, so fluorine is always -1. So we remember that. Again, right, put -1 on the halogens if you need to on your periodic table. Oxygen is almost always -2, except when it's with a peroxide or bond to fluorine. And so let's look at peroxides so you could recognize that. So a peroxide Obviously, the simplest is hydrogen peroxide. And so we could figure out the oxidation state from this one. So hydrogen is typically 1 plus, so now we have 2 plus overall. So that means this O2 has to be just 2 minus, so where each one is -1 in this peroxide. And then we could find other peroxides, so we won't go into obviously all the organic peroxide combinations, but anything with just these O, single bond O, and then R groups, right, to signify carbon or any other atom there. All right, so those are our peroxides. And then the other super important rule, so we said the oxidation state of an atom in its elemental state was 0. So again, it doesn't matter what it is, helium, oxygen, right? We have all these allotropes, don't let that confuse you. As long as it's elemental, oxidation state is 0.
I'm confused about that because number 1 says fluoride is always -1 fluoride.
But this is in a compound. So this would be elemental state. So right when it's just F2 diatomic, it's 0. And then, so ionic compound with 2 elements, typically the more electronegative element has a positive oxidation number. Oh, that sounds backwards. Oh, no, that's fine. Sorry. The metal, but it should be less electronegative. So the metal should have a positive oxidation number, we expect, and then the non-metal or more electronegative atom should have a negative oxidation number. So that makes sense, right? So that's just saying we expect fluorine to have a negative oxidation number, again, like compared to oxygen. Obviously, again, metals have a tendency to give up electrons. We're kind of seeing that trend repeated. So that's what it's alluding to. Sorry, so what's your question? So we have H2O, right?
Yeah.
And then, so all it's saying is the more electronegative one should have the negative oxidation state. So then what's the oxidation state of oxygen here? But it's in a compound. But it's not a peroxide. So what's oxygen always?
-2.
So -2, right? And then hydrogen is always usually +1. So that checks out, right, for water. Oh, yeah.
Can we find this chart anywhere else? Like, is it in the book, or should we just get it off of your
Um,
I saw it in the book, or like a truncated version.
yeah, I was gonna say, I'm not sure like where this, because I just pulled this notes like from another resource, so I'm not sure what the book says. It should mention some of these points, but yeah, this might offer greater clarification in some cases.
in the book on page 900, but it's not exactly the same. Thank you.
All right, so I'll put that, so page 900 in the textbook for, thank you. And so then, right, recall, so right, group 1 metals, obviously they're going to be +1. We've seen that, right? They have our electron configuration where they lose 1 electron and then they're back to the octet. And then, okay, group 2, again, we've seen them react, and so they always lose those 2 electrons. And then hydrogen, so we just finished saying that it's usually 1 plus, and then the only exceptions would be when it's bound to a metal, so like a metal hydride. So sodium hydrides, the most common, you could have aluminum trihydride, any sort of like iron hydrides, so all those exist. So hydrogen, -1 there. And then again, so halogens are typically -1. Again, we learned that, except for, of course, interhalogen compounds or other weird scenarios. So right when it's bound to itself, like IF3 or something, so then you'd have to go through the oxidation states. But otherwise, right, again, it's usually -1. So we've seen this with chromium, tin, right, always -1. So just these weird covalent compounds. And then mercury, if you recall, so mercury has this 1+ weird thing, right? Hg2, 2+. So just watch that. So it might have a +1 charge.
Is it always +1?
It depends on the compound. So this is, again, a common oxidation state. That's what we see in kind of the Gen Chem levels. But yeah, you could force any oxidation state. And then we have nitride. So right, any sort of our group 5, arsenide, nitride, phosphide, all those would have a -3 oxidation state. But then in compounds, you kind of have to do some math and figure out. And so that's where your periodic table could be helpful, right? Because it gives you other oxidation states, like for nitrogen, that's why it has +5. So let's check out 10 in this example. So in a polyatomic, we recall that our sum of our oxidation states has to equal the charge. And that's true in any case, right? We could be looking at a charged metal compound, same thing. Our oxidation states have to match. And then if oxygen is in our polyatomic, again, it's the most electronegative. We can assume that oxygen is -2 and then go from there. So for example, right, if we look at our nitrite, well, we know, again, oxygen has to be -2. So -2 times 3, -6. We want a -1 charge, so nitrogen has to be +5 then. And then again, you could look at your chart. You can see that's one of the potential oxidation states. That makes sense, right? Nitrogen has 5 valence electrons. Yeah, were you going to ask a question, Trinity? And then, so same thing, right, with this chlorite. So this is maybe a weird one. So we have ClO2 with a charge of -1. So again, right, oxygen has to be -2, -2 times 2, -4. And so that leaves chlorine as +3. So again, we can have some weird formal oxidation states. And so sometimes, again, it depends. So for metals, right, oxidation states are actually going to be something that you can measure and figure out, right, because you'll have a corresponding number of electrons, you'll have geometry, so you can figure out the spin of the electrons and confirm that. With some of these other compounds, right, it's kind of more of an electronic bookkeeping formality, especially with organic compounds. All right, so then going back to this formally, so what's our oxidation state of sodium here to begin with?
It's going to be +1.
It's in the solid state, so
So I guess it's 0.
yeah, so right, elemental form, so 0. And then what does chlorine start off with?
Is that also 0?
Yep, so again, elemental form, good, 0. Then reaction occurs, and they kind of gave us the hint here. But what's the oxidation state of sodium? +1, and then what's chlorine or chloride now? So -1. And then we can break this down into our half reactions. And so all that means is we've separated them by our oxidation and reduction reactions. So of course, sodium went from 0 to +1, losing an electron, so there it is on the product side. And again, just make sure that this makes sense in your head, right? You know a metal, okay, it wants to give up an electron, so that makes sense that this is what's going on, right? And you end up with a cation. Same thing with your chlorine, right? You know that chlorine's electronegative, it wants electrons, so yes, it should be gaining electrons.
I have a question. Are there any metals that form diatomic ions or atoms? Or is it just the nonmetals that are gases that do it?
Yeah, so in terms, you mean like elemental?
Yeah, because chlorine is diatomic here, but sodium isn't. Is that true of all metals? That would use to form diatomic ions?
Yeah, so they won't form like diatomics, right? So metals, it depends like what we're talking about, because if we're talking about like, you know, a sea of metals or like a metal sheet, that's kind of like different how it behaves electronically, so it doesn't really form like a diatomic element. But then that being said, right, you can still get metal-metal bonds later in compounds, but they won't be diatomics, right? So there'll be other things around them.
Different nature of bonding.
Yeah, but then, right, they can still bond. So that's important too, because there's a lot of metal-metal interaction or like metal-main-metal interaction, especially once you start to think about like catalysis and the active site and mimicking that, right? All that's really important in this. And well, yeah, not to get too far down the rabbit hole, but that like gets into why we're looking at these one electron processes, right, for metals, but when you think about catalysts, they usually do multi-step, you know, 6 electron, 8 electron processes, and that has to do with, you know, the active site, the enzymes, all that, and being able to shuttle that effectively versus just this like really simple metal, oxygen, or metal, right? So, yeah, kind of went off. Sorry, my allergies. I forgot to take allergy medication and everything's in bloom, obviously. All right, so then we separated it again to our half reactions. And this is a little picky here because we probably should have carried this 2 and distributed. They were just trying to show more of the half reactions here, but we want to think about balancing the reactions as well. And so that's something to keep in mind. Of course, it's balanced stoichiometrically. That puts us on the right path towards balancing it electronically, but we still will want to check that. So that's the added complication, too, with these redox reactions, is not only are we balancing just the basic reaction here, but we got to double check that the electrons work out. All right, so again, this is just kind of formally defining it and helping you to recognize oxidation versus reduction. So again, oxidation, our oxidation number will increase. It will lose electrons. And then potentially you can recognize it by adding oxygens. If you see more oxygens, then again, it probably underwent oxidation. That makes sense. You might lose hydrogens. Again, that could be another clue. I would still check the oxidation states, but again, these are just kind of clues. And then obviously, if you have electrons as products, that's your biggest hint. And then, so same thing, reduction. So now your oxidation number will decrease, right, as it's gaining electrons. So, and then of course, gaining electrons, you may lose oxygen, might gain hydrogen, again, other hints. And then obviously we'll have electrons as reactants. All right, so then again, we want to be able to split our reactions and kind of do our analysis. And so they've done this analysis here, but let's go through it. Because again, right, we're going to want to identify who's being oxidized, who's being reduced. And so they've gone through, so of course chlorine, right, elemental form, so 0. They didn't really tell us what this was. It doesn't really matter, right, the counter ion. And so -1 for iodide. H2O we went over earlier. So right, -2 for oxygen, +1 for hydrogen. And then looks like our chlorine goes from 0 to -1, right? So that's telling us, okay, gaining electrons, probably reduced there. And again, right, you're kind of just balancing the stoichiometry as well. So, okay, if we have 3 chlorines times 2, so 6, they're each gaining 1 electron, right? So this is a 6-electron process over here. And then let's see if that's balanced. So where did they go? Where did they come from? And so looking again at our oxidation state for this iodate now. So again, always assume oxygen is -2. So -2 times 3, -6, and then +5. So that looks good. And then, oh, now we can tell, let me change colors. So it looks like iodine, right, is going from -1 to +5 then. And so that is losing 6 electrons in that process. And again, right, okay, there's my 6 and 6. I feel good about that. And then +6 hydrogens, but that didn't change. And so again, just kind of circle, right, what changed. It should just be 2. And then, right, again, separating out our half reactions. So we went from iodide to iodate here in our 6-electron process. And then again, my criticism of this is we should really note that we had 3 equivalents of chlorine, again, so our electrons can balance.
So in this red equation, nickel reduction, is chlorine the reducing agent or the oxidizing agent?
So it's the oxidizing agent. Since it's, yeah, it's gaining electrons, right, so it underwent reduction. And then, so the other thing too that might help you with that is, again, put it in context. I handed y'all a ton of papers, and I got overexcited, and so I handed out like 2 different reduction potential graphs. I can never find one that's like really what I would like. But what you want to do is kind of orient yourself on this reduction potential, because this is all related to what we're talking about. And I don't think yours is quite labeled in the same way, but you can label it as such. And so let's take a moment to understand what this is telling us. And so these are reduction potentials, right? So that's telling us how favorable is it to add electrons. And what I like about this chart, and that's why I said, like, look at your graphs, especially the one sheet. So let me grab the one sheet. The other one, I was just overexcited and wanted you to have all the reduction potentials. But this one, the little one sheet is a handier reference just because it's more in order. And what I mean by that is, right, we have positive reduction potentials up at the top, similar to this page. And I could print out this page too. I was just trying to find easy ones to read. And so look at the terms, right? So at the top, that means fluorine is going to be an oxidizing agent, right? So it has a strong tendency to get reduced. So again, just put those terms together, because that will help you figure out like who's being oxidized, who's being reduced, right? It has to also kind of make sense, and that's where we're going today. And so pretty similarly, right, chlorine's up at the top. That makes sense. It's another halogen, so it's going to have a positive reduction potential as well, is what I'm trying to say. Bromine, again, right, I would also expect that they're all are halogens. And then what I want to point out is, okay, well, let's look at who's at the bottom and why they're at the bottom. And so, of course, these are reducing agents, again, right, meaning that they're going to supply electrons. And so this means that this is not a favorable process, right, for lithium. So we know that, right? We know how lithium behaves. It's very happy to give up the electron. And so it's not happy to add an electron, right? That's why this is so negative. But the other reaction, and this is also where we're going, is we can flip this and we can write, well, lithium solid making lithium plus and giving up an electron. Once we flip this equation, that flips the sign on this potential, and so that is a positive potential there. And so that's telling us this is a favorable process when lithium gives up the electron, right? So again, that's why we call it a reducing agent. It's down here. Again, these are reduction potentials. That's why it's at the bottom. I would much prefer them be kind of in the other way, but that's probably just my like inorganic chemist brain thinking, because I care much more about reducing agents so I could play with metals than I do about oxidizing agents. In my mind, oxidizing agents are just destroyers, but again, that's the chemist in me.
The reducing agent is what donates electrons.
Yep.
And you said lithium is most likely to give up an electron?
Well, right in this case, and just thinking about how it behaves, right? So what does lithium want to do? When you put it in water, the first thing it does is kick out the electron. Yeah. Oh, man, that reminds me. I had found a paper about sodium, and then I forgot to save it, because it's a really crazy thing what's actually happening on the surface with the water reaction. It's like ejecting electrons like instantly, and that's like why it's super explosive too and balls up and weird. But anyways, I forgot to post that paper after finding it. But yeah, so right, again, just thinking about how it behaves. So they really want to give up electrons. And so again, right, not favorable to add electrons. Obviously you can, right? That's how they mine lithium. But then you're talking about you have to put a lot of energy into that process.
So if you were to put potassium into hydroxide, would it have less of a reaction because there's extra electron?
Hydroxide,
Has an extra electron.
well, all I can say is from experience, it's the opposite. You hit it with base and you get an instant fire. I didn't do it. My colleague did. Don't try it. She lit up an entire fume hood on fire, and I had to run over and help her stamp it out. That was not fun, because there were like solvent bottles there. Like, oh, there's flames around these solvents that are flammable. And unfortunately, so now I'll have to tell the story. So this is why you always clean up your waste. So another grad student had been playing with potassium, didn't clean up the tongs properly. Other innocent grad student walks along, la la la, I'm going to borrow these tongs, hits it with a base bath, because, oh, I'm going to clean it really well. So isopropanol and a bunch of hydroxides. Boom. Fume hood's on fire. She wasn't expecting a fire. And, you know, I don't blame her, because this is always where, like, you know, you don't know what's going to happen when you have a fire until you have a fire. And especially if you're not expecting a fire. So my rule is, like, always expect a fire. So she just kind of stands there and like flips out, kind of like, oh my gosh, everything is on fire, because she wasn't. And luckily I was still in lab that day. I like fortuitously like didn't go to band practice that day. So I like ran over, zero safety equipment, and helped her like stamp out everything and like evacuate all these solvents
Was
before.
there like a fire blanket or?
We didn't, so we just like grabbed glass things and stamp it out. Yeah, like cutting the oxygen, we just like stamped it out. We'll do anything to like not pull safety equipment. But yeah, don't hit it with base. Isopropanol will light up.
It's like hydronium
Yeah, I mean, the problem is any sort of water solvent is going to make it react really vigorously. So you don't really use lithium potassium in like regular solvents. You would do them in dry solvents like benzene, but then dry means you got to dry it, aka you use sodium to actually dry it. So it's like reacting, and you already take dry solvent, what's considered appropriately dry for organic chemists, and then you dry it further. Yeah, it's quite a pain. Anyways. All right, so again, right, just kind of use this to help orient yourself logically on who's going to be giving and receiving electrons. And so this is now just like the words on how to do this, and then of course we'll practice all together. And so we're going to have to practice balancing our equations. And like I said, right, we're going to have to balance our electrons as well. So this is why we do this half method. And so you'll start by breaking down your two half reactions, so your oxidation and your reduction reactions. And so again, this is where this chart may help, and the excessive chart that I gave you may also help if you need kind of more inspiration for, these redox reactions. Because right, these are your half reactions right here, essentially. And then obviously we'll have, so electrons go on the product side of our oxidation, and then reactant side of reduction. So again, just kind of balancing them out. And then our steps will be roughly, we'll balance for atoms first, and then adjust for electrons. And so here's the more detailed, like I said, these are the instructions, and then we'll go through them. So obviously you'll assign oxidation states first. We'll write out our half reactions. Then we'll balance by our other elements. So all our non-hydrogens and oxygens. Then we'll add water where we need oxygen, add H plus where we need hydrogen. And then the last step, and again, we'll practice this, so we'll know how to do this. But if it's done in base, then our last step will be that we formally neutralize all our H plus with hydroxide, and then we'll balance our half reactions, and then add them back together.
What categorizes number 3 on this list as balancing by mass?
That's just what it means by balance the atoms. Because you could technically do mass balancing, but yeah, that's all we want to do is atom balancing. But like I said, we'll do this. All right, so let's start with this practice problem. And we'll just start by identifying what's going on. And I can already, guess who's going to be supplying the electrons just from their states. Well, let's go through them. So what's our oxidation state of aluminum? 0. And then, well, they tell us, so copper 2 plus, so 2 plus. They didn't try to trick us like writing CuCl2 or something. And then we have Al3 plus, so again, obviously that's 3 plus. And then what's copper at the end? Oh, check, but it's a 0, so back in its elemental form. Okay, so this looks good. And so now we can write out our two half reactions. So oxidized, and again, I expected it to be aluminum since it was a metal in its elemental form. So that usually again tells me, it's going to want to give up electrons, which it did. Let's write out our half reaction. So aluminum goes to aluminum 3 plus, and then show our electrons. And then now let's write our other half reaction, so our reduction.
Did you drop the kind of, state of matter when you do a conservation reaction?
I mean, I tried not to. I showed the 3 plus here, which like basically implies it's an ion in solution. And then so copper 2 plus, and then right again now balancing, so it went from 2 plus to 0. So then it had to add 2 electrons to it. And now we have copper solid. All right, so we separated it. In this case, right, balancing by our atoms is pretty trivial. We have aluminum, aluminum, copper, copper. All right. So far, no hydrogens or oxygens, right? So we don't need to do this step. So now we can skip to balancing our charges. And so what do we need to do to fix this? What's kind of our issue right now?
You're left with an extra electron on the product side.
So then how do I fix it?
Kind
Okay.
of cross multiply. So you have 3 times the reactants and then 2 times the products, and go up, add up to 6.
So get me to 6 electrons, so times 2 times 3. And so now we'll write our new half equation. So 2 aluminum solids. Oh, I don't actually want red. Stick to blue. So 2 aluminum gives us 2 aluminum 3 plus 6 electrons. And then so times 3, so 3 copper 2 plus 6 electrons gives us 3 equivalents of copper metal. All right, so now this is looking good. Now we can add our 2 half reactions. And again, right, the electrons should cancel. So I'm just going to kind of rewrite it for a second so it's explicit. 3 Cu, 2 plus, and now we can clearly see, okay, 6 electrons, 6 electrons. Again, that's just good, right? We have to be losing and gaining the same amount, obviously, for the reaction to be balanced. And so now we can write the overall balanced reaction without the electrons. So 3 equivalents of a copper 2 plus source plus 2 equivalents of aluminum metal give us 2 equivalents of aluminum 3 plus and 3 equivalents of copper metal. And so again, right, this is important, so we would know actually how to do this reaction, right? Again, we have to balance by electrons. Questions on this one?
So, can you repeat the step that cancels out the electrons again? I'm a little bit lost.
It's just when you have the same thing on opposite sides of the equation, you can cancel them out. But that's also like what we're trying to show, right? Because if the aluminum is losing these 6 electrons, right, they have to be going somewhere. So that's what we're seeing in this process. That, okay, the copper is picking up those 6 electrons.
Okay, I see. And then the third equation is us adding them together.
Yeah, since we don't need to show the electrons, right? So nothing happened overall, like net, the electrons were just transferred from one element to the other.
If you're working on a redox reaction with like more than 2 elements, like say like 4 or 6, you have to decompose it into its individual parts before doing it. And you like out the redox reactions before doing it and do all that stuff?
I mean, so you're asking about like a multiple reduction step, or?
Yeah.
Because we probably just like wouldn't do that, I guess, because that'd be like too kind of convoluted anyways, and like when chemists are looking at it, right, you're just taking one step at a time usually, like even if you're trying to like,
It's easier
let's,
to make mistakes if you don't, right?
it's not even that, it's just you got to control it. Like you can't just do, like if you put a bunch of stuff in a pot, like, you know, you'll not to cuss, but it's like shit in, shit out. Like that's a chemist saying, right? It's just like, so you kind of have to control it. And like I was saying, you know, it's not going to behave the same way like a plant does, again, with photosynthesis. And so chemists, like if you're trying to prove a catalytic cycle, you have to do either a 1 or a 2 electron process at a time. All right, probably a good time for a break. So let's take our break. You can start kind of thinking about how to solve this, but then we'll do it. All right, I think we've all made our way back. So see if you can try this on your own for a little bit, right? So we have H plus chromium metal here. So again, note our solid gives us H2 gas. So again, right, think about elemental form plus chromium 2 plus. So see if you can start that. So start telling me how it's going. So who was oxidized, who was reduced? What are our two half reactions?
Was chromium oxidized?
So chromium oxidized, good. And so how many electrons were involved in that process?
No.
One, or, because it went from like 0 to 2 plus, right?
Oh, yeah.
So plus 2 electrons. And so then doing reduce, so H plus went to H2. And then before we start figuring out how many electrons, probably just want to balance this, right? So put a 2 here, since we made H2, so we needed 2 hydrogens. And then, so if it's 2, how many electrons are involved in here? It's not 0, right? So each one, so each hydrogen goes from the oxidation state, of +1 to 0. Then we have 2 of them. So then how many electrons?
2.
Yeah, so 2. So good. And then, right, we just want to see, okay, yes, 2, 2, okay, that's already balanced. So we don't need to do anything else. And so now we should just be able to add these two half reactions together. So the reduced one, first, we just look at like the oxidation states individually, right? So do you see that we have 1 plus to 0, right? So then that itself is just 1 electron, right? But then we had 2 of them, and we had to balance it with a 2. So now, yeah, 2 times 1, so that's where we get the 2 electrons involved.
This makes hydrogen or oxygen.
Yeah, so then it'd be the oxidizing agent. Sorry, and then, so now just rewriting this, so chromium solid, plus 2 equivalents of H plus, so some sort of acid, right? And then I'll skip the electrons, since again they'll cancel, gives us H2 plus chromium 2 plus. So there's our final equation there. Questions on that one? All right, so let's try probably a trickier one. Oh, sorry, skipped a page. And so now let's try the basic solution, and we'll do this one together. And so let's just start off like before, so we need to identify who's doing what here. So our iodine, -1. What's my manganese in this compound?
It's 4 plus, looks like, or 3 plus.
Check again, because remember, oxygen's always -2.
7 plus.
Yeah, so 7 plus. Oxygen's -2 here. So, right, we all saw that. -2 times 4, -8. We're trying to get to -1, so plus 7 there.
What's the highest, like, anionic oxidation number you see in chemistry?
I mean, 7 is pretty high. I mean, 6 is also fairly common, but yeah, realistically, I don't know that I've ever seen an 8 plus oxidation state. Not saying that it can't happen, but. And then, so I2, again, elemental form, so 0. And then what's my manganese in this MnO2 now? It doesn't have a charge, though. Oh, it's in a compound, though.
On the entire molecule or just the manganese?
Yeah, so what's the oh, it's not 5. Yeah. So, right, so -2, so the whole manganese oxide is 0, right? So it has to be neutral. -2 times 2 is -4, so that leaves manganese at +4.
Sorry, why was the first one 7 plus? Yeah, I'm also confused.
So this is manganese O4 with the negative charge, right? So this has to equal -1. So then basing it off of our oxygen, so -2 times 4 is -8. So then you're trying to say x plus -8 is equal to -1. So that's where the +7 came from. Does that make sense?
Yeah.
All right, so then we have our oxidation states. So we can at least ignore oxygen. Then we have, okay, so I goes to I2. So in this case, so are we losing or gaining electrons? We got more positive though. So losing electrons. And then, right, we might have to think about doing some balancing, or you could do this in the half reaction, right? Because I like to start figuring out how many electrons, but we have a 2 here. So probably a 2. So this is this itself is 2 electrons, again with the 2 there. And then, so manganese, so then we went from a 7 to a 4 plus oxidation state. So then what happened here? Gained or lost electrons.
Looks like manganese gained 3 electrons.
So gain 3, okay. All right, so now I feel comfortable sketching this out and writing out our half reactions. And so again, right, if you're lost or get confused, we're just doing these steps, okay, right? We assigned our oxidation states. Now let's do our half reactions. We kind of did the electrons, and then we'll keep going. So oxidize, again, I'm going to put my 2I here. Gives us I2 plus 2 electrons. And then writing out our reduction, or reduced. So then manganese O4 plus 3 electrons gives us manganese 4 oxide. All right, so now we're here. And so right now this side is balanced, at least right with our atoms. So I'm going to leave this alone. Now we have to figure out how to balance this equation though, right? So we first start with our manganese. Okay, that's 1 and 1. But then we have this O4 and O2. And so let's go back. We can remind ourselves what to do. So okay, we did this step. Again, we balanced our manganese. Now it tells us to add water where we need an oxygen. So let's do that. So if I need 2 oxygens, I'm going to add 2 waters on my product side. So now I have MnO4 minus here, or manganate, plus 3 electrons gives us manganese 4 oxide plus 2 H2O. Okay, so now I have, right, 4 oxygens, and then 2 plus 2. So, okay, 4. Now we're balanced. Now going back to our instructions, okay, now we can add H plus. So now I'll just write that. So add H plus to balance hydrogens. So now on my reactant side, I'll add 4 hydrogens, right? So plus 4 hydrogens plus 3 electrons. All right, so now we're here, except this would be appropriate, right, for acidic conditions. It told us that we're in basic conditions. So that means we have to do one last step and make it basic. So basically react with hydroxide. So we're going to neutralize our H plus with hydroxide, but we'll do the same right to both sides. So let's do that. So now add OH, since we're in basic solution. So I'm going to add plus 4 hydroxides to my products, or excuse me, reactant side. And then we have to do the same to our product side. So now I'll rewrite this. Obviously this makes water. And so now MnO4 minus plus 4 H2O plus 3 electrons gives me MnO2 plus 2 H2O plus 4 hydroxide. Okay. And so now we can, what can we do from here? Do you notice something that might cancel out? So water. So now this goes away, and then this becomes 2H2O at least. Okay. So that looks a little better. And so I think we're done balancing our half reactions, at least atom-wise. Now let's go back, and we have to kind of evaluate, right, our two half reactions. So we have a 2-electron process versus a 3-electron. So what do I need to do? So cross multiply, so we can get to a 6-electron process total. So find our least common multiple, however else you want to think about it. Trying to find a good color here. So find least common multiple for electrons, or cross multiply like you said. So again, right, we're trying to get to 6 electrons total for each. So of course we'll multiply our iodine reaction times 3, this one times 2. So let me just rewrite it. So of course these can get a little tedious. So you might need extra paper, scratch work, right? Feel free to attach extra sheets for these. Yeah.
What is the second parentheses right after the, or in like the times?
Where? Sorry.
Just above what you're at, yeah.
Oh, find least common multiple?
Yeah.
Yeah, for the electrons. So just saying, right, we have 3 and 2. So we need to find our least common multiple of 3 and 2. And so I'm just still trying to rewrite. So 2 MnO4 minus plus back to 4 waters. Oops, skip my 6 electrons. All right, so now we have something that looks like this. And so now we can just add the two equations, so just kind of rewriting, and again, canceling out our electrons, nothing else to cancel out. And so then we can rewrite our final answer. So 6 equivalents of iodide plus 2 equivalents of our permanganate plus, or manganate, plus 4 equivalents of water gives us 3 equivalents of iodine and 2 equivalents of manganese for oxide plus hydroxide.
And when you're balancing the equation, is it usually easier to choose one side and do that? If you are, is there a standard for which side of the equation you balance first?
No, I mean, it just so happened in this case, this one was pretty short, right? And this one ended up being just convoluted with those oxygens, but no, I didn't really pick one over the other. Yeah, just balance them. And again, right, following those steps for each one. So again, it just so happened the iodine doesn't have any oxygens in it for those half reactions, so all that just wasn't needed. All right, so let's try it again. So take a few minutes to get at least started, and then we'll see where you're at and continue probably doing it together. And again, basic solution, but just follow those steps.
You're doing an acidic solution, you just stop the hydrogen.
Yeah, exactly. So, yeah, if we had been in acidic solution, we would have just stopped here and added the equations. Otherwise, yeah, you have to go on with the extra step. All right, let's kind of see where we're at. So did we figure out who's oxidized, who's reduced?
Looks like chlorine gains 2 electrons and chromium loses 3.
So we got chlorine gains 2 electrons, so good. So we have -2 for oxygen, so that leaves us +1 for chlorine. And then it goes to -1, so good, 2 electrons.
That makes chlorine the oxidizing agent.
Yeah, so if it's reduced, it's our oxidizing agent, it accepted electrons. So now I'm just writing the half reaction. And then, so who was oxidized then? So chromium, and then do you have the oxidation states? So what did it start off with? So this one, so we can analyze it, so we can base it off of our hydroxide. So what do we remember about the polyatomic hydroxide and what's its charge?
It's always -1.
Yeah, so if our whole hydroxide is -1, so -1, right, since we could separate it, but it's not quite proven that that's necessary yet. So -1 times 4, -4, it has -3 overall. So that leaves chromium as +3. And then what happens on this side? So what's chromium's new oxidation state?
+6.
Yeah, +6. So again, -2 for oxygen times 4, -8, but then this chromate is -2, so yeah, +6, so that looks good. So then we can write out our half reaction here. And so if it went from 3 plus to 6 plus, how many electrons were involved in that? So 3 to 6, how many electrons is that? So 3, so plus 3 electrons. All right. And so now we can do the rest of our steps for both of these. So I'm just going to start with the reduction side. Again, it doesn't matter. So going through, our chlorines are balanced, right? But now we have this random oxygen. So let's add a water to balance that. And then following, now we need to add H plus to balance our H2 here. And again, right, this would be appropriate for acidic conditions to stop here, but since it's basic, now we neutralize with OH. So now this gives us our hypochlorite plus now 2 equivalents of water plus 2 electrons. Gives us chloride plus H2O plus 2 hydroxide. And so now we could cancel out our waters at least to make that a little simpler. So now plus H2O. All right. So I'll just stop there for a second so everyone can be on the same page. All right, any questions on balancing just our 1/2 reaction so far?
I keep getting tripped up because the
Yeah, I mean, I guess because it doesn't matter necessarily like who's who, so much as the electrons are on the correct side as well, right? So even if you're getting like tripped up on the words, just make sure that the electrons balance. Does that make sense? If you know that something's reduced, then you know you need to add to it, right? If you're trying to do the reduction, then your electrons have to be on the reactant side versus the oxidation, right? Again, you're trying to show that it supplied the electrons. Yeah, and again, right, I like to think about it as being the reducing agent, but that's probably just my brain, that like the reducing agent is the easiest thing for me to identify because I'm just like, where are the electrons coming from? But yeah, as long as you're just keeping track of your electrons overall, though, that's more important. And then, so now let's just repeat this for our other side, or the side that got oxidized, or again, our reducing agent. So same process. So first, right, balancing out our chromates. And now we'll do the hydrogens. So of course, right, 4 oxygens, but I'm missing some hydrogens. So let's balance with some H+. So 4H+, plus the rest of our chromate, plus 3 electrons. And then again, right, we're in a basic solution. So now basic solution, add hydroxide. So now I have to add 4 equivalents of hydroxide to each side to balance out. So this gives us, of course, 4 waters after neutralization. All right, so this looks good so far, I believe. And so now we have, again, our 2 half reactions. I'll just kind of highlight them. And so what do we need to do now to balance and add? So what's our issue? What's our common issue? So multiply, and so we have 3 and 2 once again, so let's just do times 2 times 3, and now this just gets a little tedious to write out, and so now I'm just rewriting everything before I start, of course, balancing and canceling out any waters. So plus 3 H2O plus 6 electrons gives me 3 chloride plus 6 hydroxide. And again, just double check my work as well. It's easy to make a mistake. That's 8 hydroxide, 8 waters, 2 chromates. All right. So I think I finally at least wrote out my 2 half reactions correctly multiplied. And then now we can just cancel out what's the same on each side. So obviously the 6 electrons cancels out, but now let's deal with these waters. So 3 and 8, so 3 can go. This 8 becomes 5. Looks like I have extra hydroxides too, so this can go away. And this will become 2 hydroxide. Okay, I think that's all that we can cancel. And so now let's write our overall equation then. So now just writing everything together on the reactant side and the product side. So I have 3 equivalents of our hypochlorite still, plus 2 equivalents of hydroxide, plus my 2 equivalents of our chromium hydroxide compound. Just making sure I didn't forget anything. Gives us our 3 chlorides plus 5 waters plus our 2 chromates there. So I'll just pause there, make sure everybody writes that down, finishes, checks it, double check me too.
I got the same result.
Excellent, good. Right, everybody else okay? We're on the same page. So really, right, we're hopefully finding that this process isn't too bad, right? It can just be a little tedious. Again, give yourself plenty of paper, scratch work so you can write it all out. That's really the biggest hint for this chapter, is you might need some paper. All right, let's see how far we can get into our next kind of bit of this chapter. So, okay, now we saw, oh, sorry.
I found a quick mnemonic device I want to share. You take the word redox, the read is on the left side and ox is on the right side. And so you know that the electrons are on the left side for the read part, and the ox part is in the right, because the word kind of splits left and right. So you can kind of derive those points at which the electrons land on the split equation.
Yeah, that sounds good. There's like other mnemonics of like oil rig, like oxidation is losing, reduction is gaining. So yeah, whatever like tricks, I'd put that on your periodic table too. Any, yeah, like redox and whatever helps you. All right, so now we're gonna get into more of the math, right? Because again, we've kind of seen these reactions, we've done them, such as with the copper and the zinc. We did it with the activity series, right, of kind of exploring these reduction potentials. But now we're really going to understand what are we measuring? What are we actually truly defining when we look at this activity series? And so again, electrochemistry is just a study of redox reactions, and electrochemistry is super important and relevant. So, you know, not only is it obviously like relevant to battery technology, like that's very obvious, but again, right, if we're trying to study and make catalysts and do all these different electron processes and kind of break it down to some sort of biomimetics, we still have to have electrochemistry to kind of prove that our molecule can like survive a catalytic cycle and can actually undergo these electrochemical processes reversibly. And then we just have it defined as the conversion that's carried out between chemical energy and electrical energy is carried out in an electrochemical cell. So that's essentially what we'll be doing in lab today, is either making a cell or powering it with a battery. And so a spontaneous redox reaction is called a voltaic cell or galvanic cell. And again, right, this is essentially what a battery is. So obviously, right, that's a spontaneous redox reaction in your battery. Obviously, it's spontaneous because you stick it in and it lights up whatever electronic device you were trying to power. And then if we have something non-spontaneous, we can add electrical energy. Again, I would think about mining any sort of metals, right? What has to be done, lithium, potassium, etc. So thinking back to our lab, right, we saw that many of these reactive metals are, of course, going to be found as their oxides or hydroxides. And so, of course, to mine them, And to isolate them, right, you can apply electrical energy and then get out your metals. And so like I mentioned, again, you remember this reaction, and then you remember again that it's spontaneous in the sense that it's favorable, right? It's going to occur. And it does occur, of course, at a quick time scale. Again, I think you saw that. And this is just a little picture to remind us what happened. But then let's also look at the atomic level. So of course, again, right, we did this, recall what you did. So you had your little evaporating dish with a very similar looking blue copper 2 sulfate solution. You added a little piece of zinc, and then remember you kind of saw it rusting or turning black or something. And so that's what was going on. And then if we analyze this on kind of a more atomic level, we can think about the half reactions that were going on at the time. So again, zinc is supplying our electrons. We can see that in our redox equation here. So again, right, zinc, we gave it elemental zinc. So 0 oxidation state, and then of course it made zinc sulfate, and then zinc is also most commonly in the 2+ oxidation state. So okay, it went from 0 to 2+, again, right, giving up 2 electrons in that process. And so we can see in our little picture though where those electrons went. So those electrons went to these copper 2+ ions in solution, and then right, they formed our copper atom. So again, we see that in our equation here. So plus 2 electrons as we went from copper 2+ to copper 0. And again, right, you saw that when you were forming the rust, aka obviously the copper, but again, many of you described it as rusty looking as our copper came out. All right, so we're starting to get into, again, right, we're going to quantify this. So we'll look at this and again how to quantify the amount that we're going to make. And so obviously we have our electrical current, and so we'll again quantify it, right, with some sort of how many coulombs are passing through a given period of time. And then, right, again, those electrons are going to be supplying some reaction. So I would think about, right, how are we going to get zinc 2+ back to zinc? Well, again, right, we can pass our electrical charge through that and replate zinc. And then, again, our redox reactions involve the movement of electrons. And so that's where we can generate current. And obviously, I know you guys are excited. We'll relate it back to delta G. So, right, how can we go from our reduction potentials to then relating it to delta G? And again, right, keep in mind to be spontaneous, our delta G had to be negative, right? So that's our Gibbs free energy again. And so again, we're going to quantify this and look at more math. All right, so to make our electrochemical cell, to force it, so again, right, this is just our reaction. But we can't just make a battery like this. We can't just stick the solutions in, right? It'll just consume the copper and that'll be that. So we have to separate it to make an electrochemical cell. And again, our oxidation and reduction reactions then would be kept in separate half cells. And again, we'll see how this is constructed. And so we'll see how to make this. This will be more obvious. Actually, where's my diagram? That would be more helpful. All right, so here's our diagram, so we can go back and forth. And we may pick this up on Thursday. All right, so let's just start looking at this. And so we have, right, our two half reactions. So we have here our anode. Well, before we get into that, so right, we have our piece of metal. We'll start with that. And we have our zinc, okay? And then in solution, we need some sort of zinc 2+ ion. So right, again, here's your half cell. And metal, metal, right, your metal should match. Again, otherwise it's just going to consume it and it's not going to go through the circuit. Yeah.
Would you define the reaction as described above as corrosion, where the metal sort of deposits itself on the other one?
I mean, it depends what you want to define as corrosion, I guess, right? Because it is going to technically eat away the zinc. So like, yeah, you could say that it'd be corroding the zinc, but yeah. It's just usually corrosion is meant to talk about, like, obviously oxidation and that process. But you do bring up a point of, like, why they electroplate, like, ships and stuff and other aircraft, right, with different metal coatings to prevent oxidation or have a hardier metal on the outside. So, yeah, that goes into engineering and materials, right, trying to make it so it withstands oxidation of all the elements. All right, so there's one half side, and then we have our other, right, half reaction cell. Again, metals have to match, and then we need both sides. So we do need, right, our copper metal source here, even though we're going to be depositing more copper on, right, with the spontaneous reactions. We have to have something to plate to. Okay, so that's the first requirement. So just kind of going back to how we make our circuit. And this is what a battery looks like too. It's just those kind of, now I'm going to do like a poor explanation. But basically those half cells, they're still kept separate. They're just like not obviously two beakers. So like one reaction would be on the inside of the AA battery, and then on the outer side is your second cell. So that's how the battery works. So it's the same basic concept. And then obviously they just use like kind of more pasty materials, or they intercalate, like the lithium is lithium oxide intercalated to make it less explosive. All right, so then we had our two half cells, okay. And then let's look at the other pieces that we need, because again, we have to make a circuit. And so to complete our circuit then, so it said electrons flow through our wire, and then we also have to have a salt bridge. So let's look at this whole connection, right? So again, you're thinking about how do I complete this circuit to light up my light bulb, or if we don't have a light bulb, we would have a voltmeter to measure our potential, whether it's positive or negative. And if it's negative, right, all you either know is you swap the LEDs, or maybe it's non-spontaneous. So double check that. So then, just looking at how this would be constructed, so you would have these alligator clips, and again, you could hook it up to a light bulb if you so desired, or hook it up to a voltmeter, and then hook up, right, your other alligator clips to your other side. Okay, so that's half of your circuit. But then to complete this circuit, we have to have a salt bridge, and it can contain any salt. So, right, sodium chloride is fine. You just have to have ions, right? Because we mentioned that ions conduct electricity from their free movement in solution, right? We remember that. So this could be as simple as a like cheesecloth that's soaked in sodium chloride or something. So that would be an appropriate salt bridge. This is kind of fancier, where they have some sort of glass tubing and then have some sort of plug here. You could also, I've seen people try to make like essentially salt containing like agar solution. So like agar that would be able to conduct electricity. Like the stuff that bacteria grows on, like that gelatinous stuff. So essentially making some gelatinous stuff But for chemistry, the only problem with that, I've never used it personally. I've seen other people try. They just tend to be delicate and fall apart. But it doesn't really matter, right? Just as long as it's conducting ions.
Do the plugs on the ends there, are those semi-permeable?
Yeah, so they would have to be, so they say it's glass wool, so that would be like a cotton plug or something. So yeah, you could obviously use something more formal, like an actual membrane, right, as long as it allowed for ions to pass through. So that's our key, that again, right, ions, so we have to have the circuit complete. All right. So I think we'll probably kind of stop there. So we'll continue on Thursday. So we'll finish kind of analyzing this cell and how to make it. So there are other little things we'll talk about. And then, like I said, we'll look at this anode cathode stuff on Thursday. So we'll keep going with this topic because we still need to explain how we know that the zinc is going to be supplying our electrons and that this is a favorable process. So we'll get into the math. So we'll actually look at the quantification of these reduction potentials deeper on Thursday. All right, I'll see y'all in lab then. And again, makeup labs next week, midterm next week, so don't forget about that. And I'll hang around on stream another minute or two in case there are questions. Otherwise, again, I'll see y'all Tuesday and Thursday.
Is the midterm on Tuesday or
Thursday. So yeah, we'll review on Tuesday like we always do.
said?
Oh, it's okay. There's too many classes. But yeah, we'll do our same format. Review
Yeah.
Tuesday. Test on Thursday. I'll try to make it easier maybe.
Okay.
I'm bad at writing exams.
It's a lot of math, so that's usually what gets you.
Yeah, well,
Tuesday.
I don't know. It's too much math is my problem.
No, it's like we gotta work on the math when we study. Because personally, for me, I was doing more like theory rather than the math itself.
Oh, yeah.
So now I'm gonna like walk in and do practice problems. But
Yeah, math.
I like it honestly because once it clicks, it's fun. But on Tuesday, I can do my makeup lab, right?
Yeah,
Okay.
so, which lab did you miss?
Just the activity series.
Okay, can you just shoot me an email so I remember and
Yeah.
can still tell the stalker?
Okay, sounds good.
Okay.
Do you have the homework last week, Davey, so I can send it?
I should have it somewhere. If not, I can give it to you in lab.
Okay.